Good day everyone, I'm Dihom from Session 2. Today I will demo the tool tree for the Windows system, which is the pass performance test with version 11.1. First we go to the CPU mark page and click the advanced and choose CPU. For the block A, we need to test integer math, floating point math, and sorting algorithm. First I test the integer math and set the test length to medium, which is 6 seconds, and set the maximum test thread to 1. Set the test duration to 3 and keep the best result. I set the test duration to 1 to set time. After setting all this and click the start to start the testing. So after the test finished, we click the view graph to see the result. You can see that the result is shown in million operation per second, but we also meet as million instruction per second. And the result for the one thread is 7382.9 MOPS. And we can see our CPU name and the red at the top right corner and close the result. And now I set the maximum test thread to 16. We can see our maximum test thread in Task Manager. Choose the performance, and we can see that our logical processor is 16 for my CPU. So I set the maximum test thread to 16 and run the test again. Wait for a while for testing, and after finish, click the view graph to see the result. You can see that the result is 80,048.9 LPS. This increases a lot from one thread because it uses all the 16 logical processor in my CPU. And after test finish, we test the floating point math and set the maximum thread to 1 again and start the test. Finish, click the view graph to see the result. And also the result is also shows in MOPS. And change to 16 again. We can see that the CPU utilization is very high by running the 16 thread test. And after the test finish, the utilization is very low. After finish the floating point math, we change to sorting algorithm. And also set the maximum test thread to 1 first. And after finish the test, click the view graph. We can see that the result is shown in 1000 string per second. After see the result, set the maximum test thread to 16 and wait for a while. After finish testing and click the view graph. And also the result is also increased very large from 1 thread to 16 thread. And that's all for workload A. For workload B, we run the floating point math and vector math, which is the extend instruction. We run the floating point math first, set the maximum test thread to 1, and run the test. After finish, click the view graph to see the result. The result is 5965.0 MOPS for one thread. After this, set the maximum test thread to 16 and start the testing and wait for a while. After finish the test, click the view graph to see the result. And we can see that the result for the 16 thread also increased very large from one thread. Now test the extend instruction and set the maximum test thread to 1 first. After finish the test, click the view graph. The result is shown in million metric per second, and the result is 2774.3 million metric per second for the one thread. And now test the maximum thread to 16, start the testing and wait for a while. The test, click the view graph to see the result. And we can see that the result is non-linear compared to other tests, but the result is also increased increased very much from 1 thread to 16 thread. Let's go for the demo of the password for one test. Okay. For the analysis of the log A and B, in the integer math test, we use the million operation per second as million instruction per second, and we calculate the CPI using the clock rate divided by the million instruction per second. And this also do for the 16 thread of the integer math test. And also the floating point math test also use the same method. We use the million operation per second as million instruction per second and calculate the CPI. And for the algorithm test, we use the 1000 string per second as the million instruction per second, and also calculate the CPI using the clock rate and the million instruction per second. For the ISA structural bottleneck, the calculated CPI is limited by the CISC variable length instruction structure, and this instruction varies from 1 to 15 byte, and the hardware front-end decode this pipeline face a structural bandwidth constraint of translating a maximum of 4 instructions into micro operation per cycle. And this structural bottleneck causes the front end to fall behind the execution path of the back end for parallel ALU execution channel, and starving the pipeline and inflecting the actual CPI. The plasma performance metric demonstrate that scaling to 16 thread improves million instruction per second and reduce average CPI. And this improvement represents a shift toward throughput-oriented execution rather than a restoration of underlying ISA level structural bottleneck. In the log B, we find the SMT efficiency by the vector math test. And we calculate the float per metric first and calculate the SMT float by million metric obtained from the result times the floats per metric and divide by 1000. For the floating point unit throughput, we use the floating point map test to find it. And we find the G float by for the floating point unit throughput, we use the floating point map test to find it. And we calculate the G floats using the result 10 and divide by 1000. The password SMD and FPU throughput metric show a significant performance growth rate change from 1 to 6 thread, and this confirms that the architecture is highly effective at scaling throughput heavy vector workloads. And the result of the OLB is also confirmed that the system is built for parallelization rather than individual thread optimization.